Welcome everybody to this seminar, which is organized by Wide Bandgap Power Center. And I will start just giving you some little bit practical information, because we will not be able to control the question and answer session centrally. So I want just to inform. And we have a program which is Professor Hans-Peter Nie will introduce the speaker, and then Professor Tolbert will make presentation. And then we have a question and answer session. And there, I don't know, since I cannot assume that everybody is familiar with Teams. So when Professor Tolbert is done with his presentation, please click on this icon on the top of the screen, which is those small dolls, which is you will see all the participants on the right hand side. I will centrally mute all the microphones, but you have control of your own microphone all the time. So when you want to answer a question or ask a question, which we warmly encourage, then you press on the hand symbol, which is also on the top of the screen, and then a yellow hand will appear next to your name on the participant list. And then we trust that we all will be handling this properly. So which means that the hands will appear in the order that you are showing your interest in asking a question, and then if you take it in the order, the hands are appearing one by one, and unmute your microphone and ask the question, and then mute it again after, and please state your name and your affiliation. So things should work smoothly. So that was all I have to say. So now I will give say microphone to Professor Hans-Peter Nie to introduce the speaker.
Thank you, Mietek. So, as Mietek already told you, it is the Swedish Wide Bandgap Power Center who is the host for this seminar. But this seminar is also co-sponsored by the IEEE Power and Energy and Power Electronics chapter of Sweden. My name is Hans-Peter Nie, and I would like to give a warm welcome to the speaker today. It is Dr. Leon Tolbert, who is a professor at the Department of Electrical and Computer Engineering at the University of Tennessee, Knoxville. He is also an adjunct participant at Oak Ridge National Laboratory. Dr. Tolbert is an IEEE Fellow and has served as editor and as committee member for both the Power Electronics Society and the Industry Application Society. He conducts research in the application of wide bandgap devices to data center power supplies, multi-level converters, microgrids, medium voltage utility applications, and electric vehicles. Today, Dr. Tolbert will give a seminar on gate drive and protection for 1200 volt and 10 kilovolt silicon carbide MOSFETs. This implies high-speed switching without crosstalk or excessive overvoltages using various types of gate drivers. The seminar also covers fast overcurrent protection, high voltage power supplies, and challenges in implementing a modular multi-level converter submodule with 10 kilovolt silicon carbide MOSFETs. And again, I would like to say a warm welcome to our speaker, Professor Leon Tolbert. The floor is yours.
Thank you, Dr. Hans-Peter Nie. I really appreciated being invited to give this talk, and look forward to visiting Stockholm and Sweden again sometime in the near future when travel is better. So I'm going to try to share my presentation. I don't know where it just went. So did it share it?
Yes.
Okay. I've used Microsoft Teams some, but not in presentation mode. Okay, so can you see my full slide now?
Yes, you can.
Okay, well, thank you. And certainly if there are any issues with audio or video, speak up and we'll try to get it corrected so everybody can see what's happening here. Again, thank you for inviting me. Just to give a brief introduction about the University of Tennessee Power Electronics, we have 5 faculty now at the University of Tennessee working on power electronics: Dr. Kevin Bai, Dr. Helen Sui, Dr. Daniel Costanet, myself, and Dr. Fred Wong. And of course, we all have a little bit different areas that we work on and some overlap as well. We have one of the largest programs in power electronics and power systems at UT. We've got about 80 graduate students, and so it's one of the largest in the United States. As mentioned, we work closely with the DOE Oak Ridge National Laboratory nearby. Another unique thing is that we have a wide bandgap graduate traineeship at the University of Tennessee that's sponsored by the Department of Energy. Virginia Tech and the University of Tennessee are the 2 universities in the U.S. that have these. Ours is named or branded Potential, spelled with 2 N's like Tennessee, and there's a web page associated with that. I encourage you to go look at it. It's got quite a bit of information about some of the classes and stuff that's been offered, and there's quite a few slides available on that web page. And so we do try to focus on design-oriented coursework and training and work with several companies. And just a little bit more about this traineeship program. It's a 5-year program, and we're actually in the last year of that program. It funds U.S. citizens. We've had 27 students in the program, and 16 have completed their degrees and gone to work, and got 11 more who are still in the program. And then just to kind of show the breadth of the research that we do, you can see here that we cover quite a few areas, anywhere from consumer electronics. Let me see if I can turn on. Got consumer electronics, microgrid, smart home. Dr. Wong does quite a bit in aerospace. Dr. Bai and myself and Dr. Wong in electric vehicles. We've done a lot with utility applications, renewable energy, data centers, and Dr. Costanet's done quite a bit with medical supplies. And so power electronics, of course, is core in all of these, and it's just becoming more and more core technology. And wide bandgap is becoming more prevalent because of its advantages and able to reducing size and higher switching speed and things like that. So this is an outline of what I want to try to cover today. We're going to talk about gate drives and crosstalk. We're going to talk about some novel gate drives in addition to voltage source gate drives, but current driven and charge pump. Look at some of the issues with series connected silicon carbide MOSFETs. Just briefly touch on a highly integrated gate drive on a chip that we've done. Cover some about short circuit capability and protection, and then just kind of touch some on some of the work that we've done now with 10 kilovolt silicon carbide MOSFETs and the challenges associated with those. So just to kind of get everybody on the same page, I'm assuming that most everybody here is power electronics, but some of you may not be. This is showing a circuit for a motor drive, a 3-phase motor drive, full bridge. Basically, this is referred to as a phase leg. Motor drive, of course, drives an AC motor, and by controlling these switches, we can control the voltage through PWM that controls this motor's speed. Typically, it's connected to DC, and output is a variable frequency, variable voltage. The gate driver here, of course, is controlled by a DSP or microcontroller, and it's basically the interface between this low-level logic and the power itself. And so some of the things that we have to do with the gate drive is we need to either source or sink enough current so that we can turn on this switch, turn off this switch fairly quickly. We want to minimize switching loss. We also need to provide enough voltage so that the on-state resistance is fairly low during on-state to reduce conduction loss. And then typically there's also protection interface where we're sensing some things and we need that ability to very quickly go back over here and say, oh, we need to turn this off if we can detect a short circuit. And then to kind of focus a little bit more into the gate drive itself, and this is just showing a generalized gate driver. Basically, gate driver shown down here, but there's also other things like isolation that's needed between gate driver and the controller, isolated power supply to provide power to these things, auxiliary power supply for providing power to the controller. And as I mentioned, there's the need for protection and being able to monitor either voltage or current here and then very quickly go back and let this controller know that we need to take some action to turn things off. And so from a phase leg standpoint, it's very similar to what we've talked about. You have two input signals, typically in a phase leg. Again, you're not going to be able to short this, so you're going to have one signal and then the complement of that signal so that you have one either on and off or vice versa, off and on at all times. And the gate driver is shown there, and then there's isolation, as I mentioned, between it and this logic signal, isolated power supplies. And so again, we need to account for all of these. A lot of people in power electronics just worry about the main power circuit, but as you can see, it involves quite a bit other things that we need to worry about and work with. So what are some of the things that impact switching speed? This is showing the equivalent circuit for a MOSFET here, showing some of the parasitic capacitances and its internal gate resistance for the upper and lower device. And as you can see, the current through this gate drive here for the lower switch, when we turn it on, it jumps up very quickly, but then it falls off pretty quickly too. And so there's kind of a limit on how much current that we're able to drive because of these internal resistances here. And so we really want to see if we can maybe overcome that so that we can turn things on more quickly, hopefully. The other issue is this overshoot when things turn off. So you can see here there's this voltage across this device when it goes from on to off, and there's overshoot. We can tolerate a little bit of overshoot, but not too much. If we overshoot too much, we might exceed the voltage rating of our device and it be destroyed. That overvoltage is typically caused by parasitic inductance here in the circuit and just that current through that. And if that current change rate is too high, then again, we can end up with an overvoltage and damage our device. So much of the rest of the seminar is going to be talking about how can we improve the amount of current we can put in so we can turn it on more quickly, as well as when we turn it off, we don't want this large overshoot. And so one of the things that we worry about in device phase legs, particularly with wide bandgap, is what we refer to as crosstalk. So the same diagram that I've shown earlier, but we're going to focus in a little bit more on how crosstalk occurs. So high-speed switching and we're going to focus on this device here. It's limited by the capability of the gate driver itself, which of course we have some capability, but as we're going to see, it's also influenced by things like interference from this upper switch, meaning this switch turning on and off can end up affecting this switch, which of course is something we don't want to happen. The parasitics in our circuit and gate drive can affect us, particularly the parasitic inductance and some of the parasitic capacitances. And then the other thing we worry about is the immunity and isolation here. You know, is it able to survive some of this very fast dVdt and dIdt such that we don't damage anything? And so several different things that we're going to need to account for. So let's look at how this upper switch could influence the lower switch. Again, this is just showing that device circuit, showing that equivalent circuit for a MOSFET, and showing the parasitic capacitances that have to be charged and discharged as we turn it on and off. And there is a fairly high internal resistance in silicon carbide MOSFETs. This is not negligible. It's a few ohms. It's not something like it's milliohms or something like that. Typical gate driver is shown here on the right. Basically, you typically have a couple of voltage sources. This top one, V1, is when we turn it on, and that's this higher voltage here, which typically is something like 20 volts. And then this voltage source is when you turn it off. It's negative, maybe something like -2, could be as much as -5, and some people just use 0. Typically, there's a negative voltage there to help you turn it off more quickly, and to keep it off so that it's not susceptible to spurious noise. So let's look at how some of these parasitics and device may affect the device and its switching. So if we look at that capacitance and charge on the capacitance, the gate source capacitance, for a silicon device, it's about 169 nano coulombs. And then if we look at silicon MOSFET, it's even higher. But notice for silicon carbide MOSFET, that's fairly low. And so by having this fairly low QGS, it's able to switch much faster because you don't have as much charge that you have to get in and out. If we look at the gate source threshold voltages, you can see the silicon devices are in about 4 volts. Again, silicon carbide here, it's pretty low, about 2 volts. So that lower threshold voltage means it again turns on more quickly, but also means it's more susceptible to noise and being turned on inadvertently. And then if you look at the maximum allowable negative gate voltage, you can see silicon devices more like -20, -30. Silicon carbide MOSFET is -10. This is a number you don't really want to get close to, and because if you do, you may end up damaging your device. I think the very initial silicon carbide MOSFETs from Cree, this was actually -5 volts, and they had issues with those being damaged, and so the second generation and those going forward use -10. So as much as we talk about advantages of silicon carbide, it can turn on and off more quickly, very high thermal conduction and things like that. It can be more easily affected by crosstalk because of that high switching speed and because of some of the things that we've seen up here. So we need to minimize any of that spurious voltage that may appear here because we don't want it to affect our lower switch here. And so as we turn this off up here, and basically we're putting this voltage to 0 so that this device turns off, we don't want to end up with some high voltage across it here. And so some of the things that we can do are to try to not have all of this extra current go through here. And so one of the things that we can do is pre-charge the gate source capacitance in advance of that switching transient, or we can reduce the gate loop impedance during that switching transient. So I'm going to cover a couple of these different options here, and we're actually going to see that this second option seems to be the better one, at least in most instances. And so we're going to refer to the first one as a gate impedance regulation to try to reduce the gate impedance. And the second one we're going to refer to as gate voltage control. And these are pretty simple circuits that are added to the gate driver to just help. So the gate impedance regulation assist circuit, here's that conventional gate driver I talked about. And then here's what we add, just a very small capacitance and a small switch. These are not power devices. These are logic level type switches and stuff. So they're very small, and there's not a whole lot to those. And so again, by adding this, we're able to help use this switch and maybe bypass some of what's going on over here and actually reduce some of this resistance here, because we're bypassing this resistance when we don't need it. And then the second one is what we refer to as gate voltage control assist circuit. Again, adding to the gate driver. In this case, we're going to add a couple of switches and a diode. Again, these are logic level auxiliary transistors. They're pretty small. It's not like power devices that we're adding. So there's not a huge cost penalty or space penalty in adding these into your gate drive. And again, this is going to help us control our voltages that's applied here to our device a little bit better. And again, put it on the other side of this external gate resistance. So first, let's look at turn on transient of the lower switch in our phase leg. And we're going to look at the four options. One is we just have a traditional gate assist circuit or gate drive where we're using 20 volt turn on, 0 volt turn off. Second one, we're going to do 20 volt turn on, -2 turn off. And you can see here the DVDT for the first and the second is pretty fast. That turn on switching loss as a result of that. And so you can see that just by having this gate assist circuit, we're able to turn things on more quickly and reduce our switching losses. If we use the gate GIR assist circuit, again, pretty fast and a little bit lower turn on, so we don't have quite as much turn on losses. And then if we use the GVC assist circuit, again, you can see that we're able to do turn on even a little bit faster and lower turn on losses just because we are able to switch it faster. And notice here we don't have that need for the -2. We're able to just use a 20 and 0 volts with this circuit. Okay, so next we're going to look at turn off transient and focus on that upper switch. Again, looking at our four different options. First one is with 20 and 0, second one with 20 and -2. You can see here that -2, although we're able to, we think, well, that's pretty good, we can switch it more quickly. you can see that we're getting close to that minus 10 volts that we want to avoid. We're here already at minus 8.7, kind of a transient voltage across that gate. And so you get to be, you know, a little bit worried about damaging your gate if you can get too close to minus 10. And that's really where these other two shine. The GIR assist circuit, you can see nowhere close. You know, it's just a blip, less than a volt in terms of negative voltage. And then with the GVC assist circuit, again, very small, minus 0.9 volts. And so much less crosstalk or influence of the lower device affecting the upper device in this case when we use this sort of gate drive. So these charts here are just showing some of the tests that were done for basically different current levels. And you can see that with no gate assist, we kind of use that as our baseline and per unit 1. And then we check these other two gate assists. And you can see, at least in terms of the turn-on losses are quite a bit less, certainly at the lower current levels. And as we increase on out, still less. We can see that we're able to actually switch faster, and that's what leads to this lower turn-on losses. But a lot of times people are worried about, well, if you're switching faster, you're going to end up with overshoot, and we don't in this case. It actually is helping our device, and we actually have less overshoot than we do without it. And so it seems to be providing quite a bit of benefit to us. So just as a quick summary, both of these circuits have the ability to attenuate crosstalk, reduce our energy loss up to about 17%, improve our switching time, and not have that spurious negative gate voltage. And it just requires a few auxiliary components. And it's actually, you know, one of these is a little bit better if you're doing it at board level. One's a little bit better if you were trying to do some sort of integrated gate driver chip. So those are a couple of voltage source gate drive options. So then next, I had a student who wanted to look at current source gate drive and see if, you know, maybe we could improve on even what we've done there with the voltage source gate drive. And that was Handong Gui. Unfortunately, you know, Handong was a really good student, just a terrific researcher, published about 6 journal papers as a student, and earned his PhD in May of 2020, and then passed away unexpectedly just a couple of months later from a apparent heart attack. So really, you know, kind of devastated our group and whatnot, but at least I think Handong did some terrific work. And so the next couple of things that I'm going to talk about is mostly work that he did. So if we look at some of the turn-on loss in a silicon carbide MOSFET and compare that to a silicon MOSFET, we're going to see a couple of things kind of jump out at us. The current rise time, indicated by TCR here, is pretty about the same in terms of comparing a MOSFET between silicon carbide. But then if you look at the voltage fall time here, you can see that the voltage fall time for a silicon carbide device is actually pretty slow compared to silicon. And so this voltage fall time ends up costing us, of course. And that longer fall time really has to do with that lower transconductance, leads to a higher Miller voltage, and in effect then leads to a longer voltage fall time. So let's look at some of the limitations that appear when we talk about voltage source gate drive and some of the conventional current source gate drive. This is our typical voltage source gate drive with the 2 voltages and a couple of switches, our external gate resistance that we've added. And basically, the things that we have control over for a voltage source gate drive is this resistance, of course. Small resistance, we're going to typically switch faster. In some cases, could be too fast and lead to too high dV/dt. And so you put this in typically to slow things down a little bit. And this voltage, and that's going to influence how much current you can drive in it. However, this internal gate resistance can be a few ohms. It could be as high as 10 ohms in some cases. Could be 2 ohms, 4 ohms. So it's not negligible. So as much as we can do about this resistance, many times there's internal resistance we can't do a whole lot about. And again, I mentioned we could increase this voltage, but there's limits to that too, in terms of how much you could increase that without damaging this. This is showing that at least for the data sheet of this device from Wolfspeed, it actually showed -8 + 19 is kind of the limits that you can have for your VGS. So what we hope to do with our current source gate drive, if you remember with our voltage source gate drive, it kind of injected quite a bit of current at the beginning and then it fell off very quickly because of these internal resistance and these capacitors that you're charging. It just kind of it limits how much current you can put in, and so it takes longer. If we're able to somehow keep this gate current constant, we don't need as much time if we can do that in terms of area here. The area under this blue area and the red area is the same, and if we can keep that gate current constant, hopefully we can do it in a shorter time period. This is then showing a current source gate drive, basically a full bridge converter with inductance here in the middle to kind of serve as your current source. The reference for this is down here at the bottom. And again, this voltage though here is going to end up being limited even when we use a current source gate drive. It's because of this voltage across this is higher than this voltage here because of this gate resistance and the voltage drop across it, that current through here. And so you're kind of limited by how much voltage you can do here by DCCC here. So that large internal gate resistance means our current source gate drive doesn't really act like a current source for very long. It kind of ends up becoming more like a voltage source gate drive pretty quickly. And so our reduced switching time doesn't reduce as much as we'd hope. And so that's really what ends up happening with this existing current source gate drive. So what we would like to do is try to make it where it's a true current source or more like a real current source here, and that we don't end up with, because of voltage drop and some other issues, where it looks more like a voltage source gate drive. So we want to try to, as I mentioned, keep that acting like a current source gate drive. And it's okay for this voltage here to be higher than here, because this is what you're really worried about in terms of damaging your device. And so what we try to do here is push this VGS external to to be kind of about as close to as high as you can without damaging it, and keeping an eye on, if we know this internal resistance, then we kind of know what this internal VGS is. And so, and then our hope is after that initial switching transient here, when we're turning things on, that basically during this period, it acts more like a voltage source gate drive, so that we don't overcharge or overdrive the device. And so that's another constraint that we need to worry about. So this is showing the circuit that Handong came up with. You can see it's very similar in terms of the previous circuit with this inductance and switches, except here S2 and S3 are bidirectional switches instead of unidirectional switches, where we've put a couple of switches in anti-parallel. And we're going to see in just a second on what advantages we gain from that. So I'm going to kind of quickly run through the operating principle of this. So here you can see that during this initial stage here, T0, T1, we have S1 on and S2 on, and we can see our current is going through here. It's not going into our device at all, and so that's why we call that a pre-charging state, where basically we're charging up our inductor here. And then our gate charging state is when we turn this off and we let that current that's built up in this inductor go immediately into our gate drive, and that's shown in this section here. And you can see that external voltage, which is appearing across from here to here, you do have some overshoot, and it's, you know, pretty high voltage, but because of this extra resistance here, that actually the internal voltage VGS that we see across this device, there really isn't an overshoot, and so you're okay internally in your device. And having this bidirectional switch, it enables this VGS external doesn't get clamped, meaning doesn't get stuck at a certain voltage. It's able to get closer to this voltage up here. Freewheeling stage, we then turn on this here. And then discharge stage. This is when we're wanting to have the current be discharged out of our inductor and turn things off. So let's look at a comparison of how our current source gate drive compared to a traditional voltage source gate drive. The voltage source gate drive is shown in red, current source gate drive shown in blue. And you can see here some of the different waveforms. Let's focus first down here at the lower ones. This is showing the lower MOS and showing that turn on of the device. And you can see that current going up here in the voltage source gate drive, but in the current source gate drive, it's able to go up much more quickly because we're able to do that higher voltage. And then if we calculated the power loss, you can see here that the power loss in that initial turn on for the current source gate drive is quite a bit smaller than the area under this curve here for this voltage source gate drive. So this is for the turn on. And then the turn off, we still also have some advantage there in that the current source gate drive turn off has quite a bit less power involved in that compared to the voltage source gate drive. And so the switching time in terms of that voltage fall time, which we showed was kind of an issue with silicon carbide MOSFETs, we're able to improve on that quite a bit. So this is something that was built and tested experimentally. This is showing that 19 volts that we don't want to exceed for our VGS internal. And so this dashed blue line is the calculation of what we think that VGS internal is. And then this is that external voltage. The external voltage does exceed that limit, but the internal is below it. It's right at it. And so I think that is one of the issues. And then this is showing that the minus 8 volt was also a limit. And again, showing that at least externally we did exceed that limit, but at least internally we did not, although we came close. And so I guess one of the issues with this one is, is it okay if you're close to that limit and don't exceed it? Is that going to cause any reliability issues down the road or not? And that's something that I don't guess we've actually studied from a reliability standpoint. And this does require fairly accurate timing in terms of these turns on and turns off to make sure you don't end up with an overvoltage. So loss analysis, looking at those earlier curves that I showed you, this is showing some of these, the turn on switching time comparisons for the voltage source gate drive and current source gate drive, and you can see the voltage source turn on time is much higher than it is for the current source gate drive. And then this is showing how much loss there is in these two gate drives. There is more loss in this current source gate drive, but it's small. It's just a few milliwatts, and so compared to what you're saving in the device itself, this is almost negligible. So this is showing that switching loss comparison between the voltage source gate drive and the current source gate drive, showing for higher currents, it takes longer to turn on, but voltage source gate drive here is in the order of 20 to 30 nanoseconds, whereas with the current source gate drive, we're about 10. And notice we don't change as much also, even as our load current is changing. We're not varying quite as much, so it's a more consistent turn on time here. And then this is showing that switching loss versus current, and it's should be similar to this turn on time. This does not come for free. Of course, a current source gate drive requires that inductor, bidirectional switch, so that is adding quite a bit cost and size to that gate drive. And so that is an issue that not sure, is this something that people are willing to do in a gate drive? So one of the things that Handong and myself had thought about was, can we do something else? And is there something further that we could look at in terms of gate drives that maybe doesn't have some of those disadvantages that we saw with the current source gate drive? So the next thing we looked at was what's referred to as a charge pump gate drive. So now we've looked at voltage source gate drive and a couple of options. We've looked at current source, and now we're going to look at charge pump gate drive. So our current source gate drive, just as I mentioned a few minutes ago, we do need some accurate control signal. We require some bidirectional switches and this fairly large inductor here that we've added to our gate drive. And so what we would really like is, of course, not to have that inductor and some of those things. So, this is kind of an idealized sense of what we would like things to look at. We would like our gate drive supply voltage to be increased so we can provide more current. And just as I mentioned, it's okay if this voltage here is higher than this voltage here. But after that initial voltage, we want it to kind of return and be more of the traditional voltage. So this is, you know, some people also refer to this as a multi-level gate drive voltage, where instead of just having a single, you go from 0 to 20 volts. Well, you do this higher voltage for some time and then drop back down to this other voltage, but it's still a little bit different. So our charge pump gate drive circuit is shown here. The traditional gate drive is shown right here, where you have these two switches and your voltage sources. But what we've done here is added this charge pump in the middle. Charge pump requires some logic level circuit in terms of switches, a couple of small diodes, and some capacitances. But of course, these capacitors are quite a bit smaller than that inductor that we saw for the current source gate drive. And so again, we will kind of run through how this one works. So initially, before we try to drive this, you know, it's the lower switch is on, so we're connected to the negative voltage and our main power device is off. And what we're going to do is charge up these capacitors here, CP, CF. So we're charging these up so that we're getting ready to use the energy we store here and dump that into our gate drive, just like we did with the inductor. Remember, with the inductor, we charged it up and then kind of dumped it in. Well, but in this case, we're using capacitors. Again, we've charged these up, transfer a little bit more charge from this one to this one, try to get this one pumped up as high as we can. And basically, this circuit is allowing this voltage here to be almost equal to twice this voltage here. So we're able to get quite a bit higher voltage here than what we have from just our power supply, almost double. And so once everything's ready, we kind of disconnect this from this. And now we're ready to dump that power in and use that in our gate drive circuit. So we've charged this up, got ready, and then we dump that in. And so now let's kind of take a look over here at our waveforms. Again, you can see that our voltage that we've applied to our device here is quite a bit higher. It's quite a bit higher than a typical gate drive voltage. But yet this voltage that we see internally, VGS, it's not. So we're not worried about damaging this device. We have a very high voltage externally, but we don't have, because of the voltage drop that you see across this, we don't have that really high voltage internally. And then once, you know, the internal capacitances and stuff are kind of charged up, we switch out of this and switch back over to VDR into that lower voltage level. So again, we switch to this higher voltage level, but then we switch back down to this I call intermediate or on state gate driving voltage. So some of the things that you have to pay attention to with this charge pump gate drive are your selection of these capacitors, CP and CF, particularly CP. It needs to be large enough to store enough charge such that it can, when you do that charge jump, that it provides enough to that and it really does improve your switching speed. So you want it big enough, but not too big, and not too small, just right. And so you can do some design to determine what that should be. If it's too large, again, this does not drop down, and maybe this ends up taking too long, and you could end up overcharging this CGS and end up damaging your device. So can't be too small, can't be too large. It needs to be just so to speak, somewhere in between the two, where you don't have any issues with that. This equation here is showing how to determine CP. And we know all of these values from device data sheet or from choices that we've made from our gate drive voltage. And so we can calculate what size capacitance works best. So our prototype charge pump gate drive is shown here. This is showing the board here, showing the divided into the gate drive part of it, the charge pump part of it, and then the isolation and power supply. And we tested it for a couple of different devices, silicon carbide MOSFETs here, a little bit different current ratings, a little bit different internal gate resistances, and the same thing, they have a little bit different values for CGS as well. And so this is then showing, I mentioned those choices of CP, one a little bit too large, one a little bit too small, but again, just right, is it's only 1.8 nanofarad. So this capacitance that we're using in our charge pump, it's pretty small. It's not something that's really big. And then this is showing for these different external voltage that or external resistance, I meant to say, that we add to our circuit. And so by increasing this RG external, you're able to not have this overshoot necessarily, if that's something that you're worried about. Showing some additional test waveforms. Again, red is the voltage source, blue is the charge pump gate drive. And it's again showing that power in the charge pump gate drive is quite a bit less than the voltage source gate drive. This is then showing, using these different external resistances, how that slows things down, of course, as you add those, just as it does in a traditional gate drive circuit. And then this is showing it for the device B, the higher current rated device. You can see there's not quite as much oscillation in these circuits because there is a higher capacitance internally that's got to be charged, but you can see much lower switching time for the charge pump gate drive. It just switches much faster. So if we show a switching loss comparison between these, you can see that at least on the left, for the charge pump gate drive is shown in these colors, blue, green, yellow, red, with different external resistances that have been added. And of course, as you add that resistance, it slows down and our loss becomes higher. Voltage source gate drive is shown here. And so you can see that our charge pump with a very high external resistance is just like a voltage source gate drive. Our current source gate drive is in purple here, dashed line. And you can see it's kind of similar to our charge pump gate drive with that 5 ohm external resistance. So we can improve on that current source, be about the same with 5 ohms, or if you're willing to go to a smaller external resistance, you can switch it even faster and have lower loss. This is for device A, and then device B, very similar. We did not use the current source gate drive for this device B, but again, comparing these three versus the voltage source, you can see they're all pretty much better. But of course, you know, there's always trade-offs. I think this is something that at least when I talk to students, you know, there's in power electronics and gate drives, device selection, always seems to be trade-offs. You don't, very rarely do you get something for free or get something without end up affecting you in a bad way. And so, you know, there is a trade-off, that higher switching speed and any side effect from parasitics. But you can, by controlling that gate resistance, make sure that you're limiting things within an acceptable range. And at least the switching loss of this CPG, even if you use something larger like 10 ohm gate resistance, it's still going to be less than the voltage source gate drive. And so that charge pump gate drive, again, it's able to provide quite a bit of current by charging up that external capacitance and then just dumping it in. It's fairly simple structure, not a lot of extra control or signals or anything like that. So maybe let me pause right here and take a few questions here, kind of, I'll call it at an intermediate state. While I'm in presentation view, I can't really see people's hands or things like that, but maybe if somebody had a question that they wanted to ask right now, can go ahead and do that.
Please go ahead, Frederick.
Okay, can you hear me okay?
I can hear you.
Yep. So I had a question on, you talked about these different concepts with the GVC and the GIR and then the negative turn-off voltage. Can those concepts be combined with the negative turn-off voltage to reach even better speeds?
And I understand your question there, and I think that probably is a possibility in terms of, yeah, the GVC and GIR only use the zero voltage, I guess, just to be simple. And I don't know, for whatever reason, I don't think we went on and explored using a negative voltage in combination with those. So that may be something that somebody needs to check and see if that provides yet some additional benefit. And I think that can be kind of said for these gate drive in general. Is the reason we've done quite a bit of work in this area is we kind of tried to study how does gate drives work in detail, and then, okay, well, what do you need to do to improve on that? And so I think there's still more work that can be done, of course.
Yeah. So I'm sorry, I forgot to mention my name. My name is Fredrik Allerstam, and I'm with On Semiconductor. The reason I ask this question is because you brought up these ratings, which are sometimes much more narrow on the silicon carbide MOSFETs. And we are, of course, from our side, making the power switch, interested in where should we put our focus in improving the device. And do you see a great benefit from us making a device which has a broader negative rating, say that can go to maybe -15 or something like this?
I do, and I think from that perspective, just from a reliability standpoint, then we're able to try to switch it off more quickly and not be worried about how that affects that. If it's something that, again, we get back into this trade-offs. Does making it -15? I don't know what penalties are incurred in some other areas, and so. But I do like where you're going with this, because I do think device manufacturers and our device application people do need to work hand in hand to say, hey, if you could do this, it would, help us. And sometimes these things can be done fairly easily, and sometimes they can't.
Yeah. I guess it depends very much on the application, right? Because even just generating the negative voltage for the drive itself is sometimes something that the designer wants to avoid. But okay.
Right. Yeah. Sometimes they don't want that extra power supply to generate that negative voltage. Yes.
Yep. Thank you for the answers.
Good questions and good commentary. Anybody else have something they want to ask on this section? I've got quite a bit more to talk about, but I thought that it would be good to have a short pause here, allow a few questions.
I have one question. It's Kent Bertilsson. Can the switching be optimized further if you're not using the same charge pump capacitor for different gate drive resistors? Or are they always?
That's that's a good question too. I think that is something that you could look at and see if I said, okay, you choose this certain capacitance and that helps you to dump in a certain amount, but yes, the RG is part of that, and so you may want to very well change that capacitance based on your external resistance as well, as opposed to, well, I do all my calculation for CG and then I just start playing with RG at the end. You probably want to consider those two simultaneously.
Okay, thank you.
Any other questions? Okay, well.
Per, go ahead.
Yes.
I see that you are raising hand, but you are muted. You have to unmute yourself.
Now, might be better. Good. My name is Per Ronstad. I'm involved in quite many research projects on applications. So this is very interesting to hear. Would you comment on your research results on the gate drives and relate them to soft switching converters? I assume that your application is mostly hard switching here.
That is correct. And I think a lot of what we've looked at was that, at least with silicon carbide and its unique characteristics, that we could do hard switching to a large degree and not have to worry about all the additional complications that come about when you do soft switching. And so we've kind of focused mostly on phase legs as well, because most of our applications have been inverters and looking at things like motor drives or just utility inverters connected to the grid and whatnot. For soft switching, we have done a little bit of work, at least in my students. Dr. Costanet has done a lot more in that area because he's doing GaN mostly, and really high switching speeds, you know, megahertz type of applications where you have to do soft switching. And I think have done some, if you want to call it similar, like charge pump gate drive, but it's for soft switching. And so there's quite a few other things that you have to think about in addition to soft switching. There's things such as sometimes the soft switching only works over a certain load range and things like that. And he's worked on some ways to widen that load range where you can soft switch over a wider range. And you have to, the timing is very critical in these very fast switching like GaN, such that you are soft switching all the time, but you're also having to make sure you're in that resonance and whatnot. So yes, I do think if you want to do soft switching, you can, and I think you have to with things like GaN. With silicon carbide, we haven't had to, but we have not explored really doing soft switching to a large degree with silicon carbide. That may be something that some folks could look at to see if that gives you some gains without incurring too much additional complexity or devices.
Okay, thanks.
Any other questions before I move on to the second part of this? Okay, well, I think that was kind of a good little pause there, and I'm going to even stand up for just a second to. I'm usually used to standing up when I give these talks, so okay. Next, we're going to talk about a few, I'll call it odds and ends, but still you'll kind of see how gate drive keeps coming back to play in all of these different things. One is series connection of silicon carbide MOSFETs. It's not something typically people think about because usually with higher voltage they use some sort of other device like thyristor or IGBT. But with silicon carbide MOSFETs, it may very well be something that if you're wanting to go to higher voltages, you may need to ponder how do I use these. And so, of course, voltage imbalance is an issue. If you have an unbalanced voltage, you could end up damaging it. It's typically not too hard to maintain voltage balance during on state, during off state, of course, in particular, that you're concerned about. But the key then is that turn on and turn off. How do you make sure that that's balanced? Some of the things that can lead to unbalance, certainly your gate drive, if they're not synchronized well and whatnot, any asymmetry in those could lead to unbalance. The devices themselves, the silicon carbide MOSFETs, at least early on, there was quite a bit of variation in things like threshold voltage and some of those internal resistances and capacitances. I think there's less parameter mismatch as they get more mature, but still could be some. And then just general parasitics in your circuit, any parasitics there, if they're not all the same and your traces the same length and width and things like that could lead to mismatch. So somebody else started sharing, maybe accidentally. Okay, let's make sure you can see my screen again.
Yes, you are back now. You are back.
Okay. So this is showing instead of a phase leg, basically devices in series. So let's change our mindset just a little bit here. Instead of wanting these to switch complementary, we're wanting them to switch identically at the same time, meaning we want both of these to turn on, turn off at exactly the same time. What this is showing here is that these two devices, the lower device, the upper device, as they turn off, that actually they don't turn off at the exact same instant. You can see one of them turns off more quickly than the second one. And the one that turns off more quickly ends up at a higher voltage. It's blocking more voltage because it turned off faster than the second one. And that's not what we want. So what we could do, because this lower one turned off more quickly, what if we delay its turn off intentionally? We need to change our gate drive just a little bit, by a nanosecond or 2 nanoseconds or something. We need to delay it so that hopefully these two match. And so by having that little bit of delay, you can see now our lower device and our upper device, those waveforms that turn off looks pretty good. They're about the same. And now our voltage is well balanced. And so the basic idea is what's referred to as high precision gate signal timing. Be able to adjust this gate signal, either advance it or delay it just a little bit to make sure that they're all about the same. But be able to not just tune these in one-time tuning, but be able to do this dynamically is really what the challenge is. Same thing here, at least in this case, showing the lower and upper device. And in this case, the upper device is switching a little bit more quickly, turning off more quickly. So now the upper device has a higher voltage blocking. Lower device less, because it was slower. It kind of turned off second. So we need to move this gate signal to the left this time, meaning advance it a little bit. Instead of delay it, we need to advance it, make it turn more quickly. And you can see by doing that, again, we can get things to be well balanced. So we just need to be able, these gate edges, adjust those a little bit. And how much is that little bit? It's about a nanosecond, and that's why it's referred to as high precision. It's not microseconds, it's nanoseconds. So this is then showing again that voltage imbalance and showing that in this case quite a bit of unbalance. And this is in the turn on case. Earlier we looked at turn off case. So even turn on, a lot of people say, well, what are you worried about there? There shouldn't be a whole lot of voltage once they've turned on, but just dynamically, there's quite a bit of difference. But again, if we can do a little bit of adjustment at that turn on point, you can see we end up with where we don't have any dynamic voltage difference between the two devices. Same thing here, where again, one of them is turning on a little bit quicker. We're wanting instead to advance this lower one a little bit because it was a little bit slower than the top one. and again, get it where it matches. And again, that's about a nanosecond. So, conceptual diagram, it looks pretty busy here, but I'm going to try to separate it into the different sections. If we start here on the right, this is basically sensing our voltage imbalance and determining our dynamic voltage balance, sending that back through a signal isolator, and basically we're needing to dynamically adjust either the turn on, which is this rising edge, or our turn off, which is this falling edge. And those are, the two adjustments that are needed. Once those adjustments are made, then of course it goes back through our traditional gate drive circuit. The other thing that we've added here are these transient voltage suppression diodes, and I'll talk briefly about those too. And this is just highlighting the different things that I just talked about. Okay, so again, this very high resolution tunable gate drive signal timing circuit. This is showing an adjustment. We couldn't quite do a nanosecond. I think what we did was about 1.5 nanoseconds, and showing that we could adjust that in about 1.5 nanosecond increments. The upper switch is here, and then the lower switch, we could either do it this direction or this direction a little bit. And our DSP actually had a resolution of about 0.1 nanosecond resolution. So we're able to make that adjustment as needed. Same thing here with, again, just able to adjust it, the turn on as well, which is shown here, and the turn off, which was shown here. The transient voltage suppression diodes, again, that's just to clamp that voltage to make sure we don't exceed the breakdown voltage over our temperature range. So basically, you look at what is the breakdown voltage rating of your device over a junction temperature range, and you add these diodes and make sure their rating is a little bit less than whatever this rating is. If this is 600, maybe use something like 500, just to make sure you don't get close. So it's just some additional protection that you could add if you're concerned. So again, this was just another little project that we did looking at if you had series devices. Another thing that we did, and this is some work that we did actually several years ago, was how could we integrate gate drives into just a device on a chip. And at that time, we were looking at high temperature applications, something like 200 degrees C ambient, and so we looked at something called silicon on insulator, SOI based gate drive. And basically, using this SOI gate driver, we could put all kinds of functions into a very small area. You can see here this is about 8,000 micrometers, or 8 millimeter by about 4 or 5 millimeters, so very small. And we could put our core gate driver with charge pump on a chip. Things like temperature sensor, short circuit protection, DSAT protection, gate current monitoring, under voltage lockout, some voltage regulators. So this is not something that, at least as a power electronics person, I was familiar with, but I worked with Ben Blaylock, who was very familiar with electronics and integrated circuits. And so we were able to put lots of stuff in a very small area. It really shocked me as a power electronics person how much we could put in this integrated chip. So we put all of these different functions, and we're able to drive a current of about 5 amps. And that really ended up being kind of a couple of limitations was we could only do up to about a 5 amp gate drive, which is fine for many applications, but not real high power applications. And our switching frequency, we could do up to 100 kilohertz, maybe 140 kilohertz, which again, power electronics, that's pretty good, at least for silicon and maybe even silicon carbide. Not so much if you're wanting to do something like GaN. But we also made it where we called it universal because we could switch many different types of chip power devices. So this is then going to show it more from kind of a circuit standpoint, all of these different things that we integrated there, and basically just different blocks of control, dead time, edge detecting, level shifting, charge pump, volt. So all of these different things, we just, were able to integrate it. We tried it out with several different devices, including MOSFETs, which at that time, something like 0 to 20 volts, some of the normally off JFET that was available from Semi-South had this kind of variation. The SJT from Genesic 0 to 50, which is basically a BJT or an IGBT. So we were able to test it on all these different devices over a wide temperature range, and it was a pretty good product, at least I thought. Fairly rugged. So again, that's something for people to consider when they're doing some of these advanced gate drives, and you think, well, I had to add this, add that. But if you're going to do an integrated chip, it doesn't really matter if you've added all these things. If you've checked it out really well and it works okay, once you're integrating that into a single chip, some of these intelligent gate drives and stuff, not really going to cost that much. So another thing I wanted to talk about was short circuit protection. We've kind of just talked about driving it, but we haven't really talked about looking at short circuits in silicon carbide MOSFETs. So let's look at that next here. And here are some of the references from some of the earlier work. Short circuit capability testing, looking at Cree, looking at Rohm device. These are some older devices, actually. This was some work that was done, probably 6-7 years ago. Device under test. This is your typical double pulse test circuit, but we've added something here like a solid state circuit breaker because we are going to be doing short circuit protection and we don't want to damage our test setup. And so looking at these devices, it's basically a what we refer to as a delayed failure mode, meaning we run a short circuit current for a little while and we go ahead and switch that off, but the device actually ends up failing even after we've turned it off. As you can see here, we started out with a short circuit current that had a duration of 5 microseconds. Here, 5 microseconds, and it was fine. We did 7, 9, 10, and then when we got to 11, 12 microseconds, or you can see that we ended up later, the device failed. We turned it off, and then just 3 or 4 microseconds later, it failed. Same thing with 13 microseconds. It failed, but failed more quickly. So that's what's referred to as the delayed failure, meaning you ran your short circuit current through it, you turned it off, but just that heat, it took it a little bit until it reached something and damaged something. Same thing here with the second generation, still had failures. Actually, the second generation devices failed even more quickly than the first generation. And that was because these devices were smaller. Their surface area is smaller, so that they just had nowhere for this heat to go. And so that leakage current increased at a even less time in these new devices. With Rome, the behavior was similar to the Cree devices, but the Rome have a longer short circuit withstand time. So they are able to tolerate closer to 17 microseconds at 25 degrees C. But then if you have a higher temperature, 200 degrees C, well, they're not able to tolerate as much, maybe 13. And that makes sense. If you're starting out at a higher temperature to start with, that short circuit current does not take as much time to then push it on up to a temperature that damages the device. If you're starting out at a lower temperature like 25, it should take longer to heat that device up to where you have a failure. And so to compare what we refer to as short circuit withstand time for these devices, the left side here is looking at with a 600 volt DC link for these 1200 volt devices, and we compare the Rome and these two early version of Cree, and you can see that at least with the Rome device here, they had a longer short circuit withstand time, about 14, compared to the Cree devices, which were 10 and 8. And then down here was that critical energy, which is higher for the Rome device. And then on the right is looking at 200 degrees C case temperature, and then looking at different voltages. And again, the Rome device just has a little bit longer short circuit withstand time. You can see that as you increase that voltage, the withstand time goes down because, again, you're dissipating more power when you have that higher voltage device. I am not a device person. I am really an application person, but at least this is kind of talking about how we think that failure mechanism occurs. Basically, it's a temperature-dependent leakage current model. It's dependent on things like intrinsic carrier concentration, electron mobility, lifetime, diffusion length. Can put all of these things into our model, and you can look at it from a single event, or you could look at it more from a degradation where you just repetitively are doing things, and it's not something that fails immediately, but as you repetitively do something, it slowly degrades and then eventually fails. And so again, looking at this more from a repetitive business, you can see here that looking at least from this Cree device at 750 volts, you're going to end up with higher temperature and things are going to fail more quickly than at a lower voltage device, and lower voltage, lower temperature. And some of the things that you have to worry about are thermal runaway, leakage current surge, metallization degradation, ohmic contact passivation, and gate oxide degradation. So several things you need to worry about if you're really going to get into looking at robustness of devices during short circuit and things like that. So, you know, the short circuit capability is reduced when you have higher current density. And so that is a disadvantage of silicon carbide compared to silicon. Short circuit capability is much less for silicon carbide devices. And so it's been something that I think has limited its usage, because some people are saying, well, we need it to be more rugged and for things like short circuit currents. And the mechanisms there, some of the things you worry about are the thermal runaway or the gate oxide damage. And so that is something that's concerned about, and why we then started looking at protection. As I mentioned, it's more challenging in these devices. There's lower short circuit withstand capability. They have, in some cases, long-term issues with gate oxide degradation. Basically, the summary of all of this is we need to be as fast as possible. If there is truly a short, you want to interrupt it very quickly to minimize any damage or destruction or degradation. And so some of the things that you worry about with protection schemes is that single event or repetitive, as we've talked about. We noted that for those devices, looks like we need to be able to interrupt less than 5 microseconds if it's a single event. However, if it's something that seems to be occurring pretty often, repetitive event, you may need to be as short as 300 nanoseconds so that you're not damaging your gate oxide reliability. Well, that's a whole order of magnitude different here, isn't it? In silicon IGBTs, typically we're trying to interrupt things in about 10 microseconds. And if you can do it less than 10 microseconds, that's usually okay. And what we're saying with silicon carbide MOSFETs, you're needing to do things much faster, maybe less than 300 nanoseconds. The other thing we worry about is noise immunity. You do not want to have any false triggering here, meaning you don't want it to think that you had a short circuit when you're turning something off or turn it on. And so you really want to have some sort of capability or delay to make sure that you have a short circuit and that you're not interrupting things when there really wasn't an issue. It was just some noise. So one of my students looked at some different protection schemes like solid state circuit breaker, DSAT technique, and then something he called fault current evaluation. All of these were able to be pretty quick, able to protect in less than 200 nanoseconds. We mentioned the 300 nanoseconds was our goal, and so they all were able to meet that goal. Solid state circuit breaker is basically external to everything. It's not part of your gate drive or part of this. It's kind of in your external circuit. It could be either put in this position B, which may end up causing additional power dissipation, or it could be here in position A, less power dissipation, but maybe not quite as good in terms of reliability standpoint. Again, this had a fairly fast response time to any kind of a short circuit. It was able to respond in about 120 nanoseconds for hard switch fault or fault under load, and completely cleared the fault within 200, 250 nanoseconds. DSAT, as I mentioned, was another alternative, and this is one that a lot of people use today. It's basically where you're monitoring the output voltage of the device, the VCE of the device, or VDS, depending how you refer to that. And typically during an on state, that voltage is supposed to be pretty low, right? It's supposed to be, a volt, maybe 2 at most. And so if that ends up being something like 3 or 4 volts, because you have very high current, then you're basically had a short and you need to take some action. And so the DSAT technique, of course, had been used quite a bit for silicon IGBTs, and so we wanted to check if that would work for silicon carbide MOSFET and be able to work much faster and still have noise immunity and whatnot. And basically able to do there is add some additional logic here and then have this DSAT detection circuit here. So this part is basically to monitor that voltage across our power device. And then this is to basically process that signal and to say, hey, you're a little bit too high, and send a signal here to turn off, or to say it's okay and provide the traditional PWM gate drive. Also, one of the things we have to worry about during a short circuit is turning it off too quickly. And that may sound like, well, if you have a short, you need to turn it off very quickly. Yes, but if you turn it off too quickly, that very high DI/dt could end up damaging your device because of LDI/dt. Any parasitic inductance that you have, which is the L times DI/dt, could lead to an overvoltage in the device. We're worried about current, but you will have an overshoot as you turn that off. If you turn it off too fast, that overshoot could damage the device. So we have to have what's referred to as a soft turnoff, meaning you don't just immediately interrupt your current, but you kind of clamp your voltage or clamp your current and then let it turn off over some period of time. And so we were able to, with a DSAT, have about a 210 nanosecond delay. And that 210 nanosecond delay involves several things. There's a blanking time. This blanking time was put in basically to kind of make sure it's not just noise, that we did really have something. So we have that blanking time in there. Then we have that comparator response to say, okay, yes, we've exceeded, and that we have some delay in our logic signals. And so this is, again, just showing kind of how all that works together with your DSAT detection and how that is able then to be detected. And then also our protection threshold, it's also temperature dependent. So you do worry about, is this going to work over a wide temperature range, a wide current range? So you kind of have to think about all of these things. You can't just design it for a single operating point unless you're some kind of application that only runs at a single operating point. You do need to consider all of the operating points that you operate at. And so we looked at things like from 25 degrees C all the way to 200 degrees C and over different things, and then kind of where should our protection be set at. And we pretty much said, well, probably if you get more than 5 volts drain to source, then probably that's going to be your issue there. And so we set our threshold as a 5 volt VCE or VDS as something. And once we exceed that, that's when we want something to happen. So your short might start here, but then you don't exceed your threshold until here. Once that exceeded, then it takes a little bit of time for that to be detected and to take action and then to turn things off. You can see the soft turn off here. And so what's referred to as the active protection, fault current evaluation protection scheme, that's shown here. Again, it's very similar to the DSAT, but instead of monitoring this voltage, we're actually just monitoring current. So again, you can monitor the voltage across the device, or you can monitor the current through the device. In this case, monitoring the current through the device. What was nice about this is we did not need that blinking time. And it's actually a little bit more immune to noise than the DSAT protection scheme. But it is very similar in that you have some fault current to detection, some logic associated with it. You still have that gate voltage clamping. You still have the soft turn off. So it's very similar to the DSAT, except that we're monitoring current as opposed to the voltage. This is showing, again, we're monitoring this current here. We've got some circuitry. Again, this is not power devices. These are all logic level devices, pretty small things. It's able to decide, are you in a normal mode or are you in a fault mode? And if you're in a fault mode, it will trigger some of the other things that you have to do. And so that fault current is almost proportional to a capacitor voltage here inside our monitoring circuit. And so just by monitoring that, we can kind of tell if we need to do something. And then this is basically the mode of, activate, deactivate our protection mode. This is our clamping part of that. Make sure we don't allow voltage to go too high or our current to go too high. And then this is what forces our gate driver output to go low. But as we make this go low, we actually want to increase our gate resistance. So that's where this added soft turn off, our soft, increase the gate resistance to reduce that turn off over voltage. This is showing some testing results here. Total protection delay here is about 140 nanoseconds. On the right here, about 170 nanoseconds. These are for the two different types of fault you typically consider. Hard switching fault means the fault is there and you switch into it. Fault under load means you were okay, the thing was on, and then the fault occurred kind of while you were running or on. And the total delay time for these two are well under the 300 nanoseconds and actually less than 200 nanoseconds, about 140 nanoseconds and 170 nanoseconds here. So these protection technique comparison, very fast for all of them. You could see all of them were less than 300 nanoseconds. Power dissipation, a little bit, the solid state circuit breaker, you kind of have some losses all the time here. These other two, not so much. Nice thing with solid state circuit breaker, it's kind of external to the device. You just stick it in your circuit. These other two, not as much generalization. You kind of have to look at the switch that you're using and things like that. And Complexity a little bit more too. Cost is a little bit cheaper with these though. They're just some logic level things, where solid state circuit breaker is going to cost more. So again, your protection with silicon carbide MOSFETs, at least for the 1200 volt devices, has to be about 300 nanoseconds, which is much faster than silicon IGBTs. But that's within our capability, and we can do that. So you just have to not say, well, this doesn't work. No, you just have to design something that's faster and works with these devices. And so these are some references associated with that work. And so in the interest of time, I'm probably going to stop here. I had mentioned before I started that had some high voltage work, but I think may not be able to cover that today, and I have to do that some other time in a few months from now or something. Can maybe just do a short thing related to high voltage devices. So I think I'm going to just stop right here and take some questions about short circuit interruption, or the first part, if somebody had a question that they just didn't ask on some of the earlier part.
Yeah, I will maybe take another question then. Can
Sure.
you hear me? Yeah,
I can.
This is again Fredrik Allestam from Semiconductor. I wonder, do you have a reference to this, what you showed in terms of this degradation in MOSFETs? You showed quite a nice spread of different failure modes that you go through in terms of time in short circuit.
Yes, and I believe it's probably this top one shown here. At least that's showing the temperature dependent short circuit capability. It was published as a journal paper here in 2016, and probably as a conference paper maybe a year or two before that. So I think this might be something you would want to look at.
Yeah. Okay, thank you. Then I also wondered, I may have missed it when you talked about it, but what about isolation for this integrated gate driver that you made?
Yes, you didn't miss it, but because I didn't talk about it. And, so that integrated gate driver circuit, I'm trying to think back to, because isolation was an issue. I want to say we were able to have isolation, I think it was around 2 kV, 2 kilovolts. Mm-hmm. And so it was fine for that. I think it was work that I really enjoyed, but we haven't worked on it any time recently. And I think it's because some of the funding went away, as well as some of the manufacturing kind of went away to some degree. It was at Atmel, which became Telefunken. Mm-hmm. And I'm not sure if that SOI process, if they still have it there. I think in the United States, there is still a couple of places that have similar processes, but they were very expensive at the time, at least for us as a university. And
right.
And that led to us not doing further work in that area.
Mm. But this means then that you're able to use it both for the high and low side using the same process?
Yes. Mm. Yes, we were. and we were able to, the two rails, meaning, you know, I think we designed it where it could go anywhere from -10 to as high as 30, if I remember. We did several iterations of those. We did about 4 different integrated gate driver chips, and we kept trying to push up the amount of current that we could drive. I think the initial ones maybe could only do about 2 amps, and then later, and maybe it couldn't do it continuously, and then later we could do 4 or 5. And so, and we added some capability in each time we did a new integrated gate drive. The tongue twister. The integrated gate drive. I think I've got that, at least one of those papers listed here. Let me see if it's up here at the beginning. Yeah. That's this paper down here at the bottom, 200 degree C universal gate driver for integrated circuits. That's probably the best one that hopefully references some of our earlier papers as well. But again, we have not done a lot of work in that area since 22. I say a lot. We've continued to do some in integrated gate drive. We've used it and integrated it with some other things, but at least this kind of talked about the capabilities, and then we've kind of used it more in an application basis later.
Okay, yeah, thank you. Yeah, I think those were all the questions I had at this time.
Sure.
Thanks again.
Well, this is Muhammad Nawaz from ABB. Hello.
Hello, good afternoon.
Yes, good afternoon, sir. The question is, did you have some experimentation on the paralleling of these SiC MOSFETs? And then if we have some short circuit in one of the switch. So any experiment you have performed like that?
So I did have one student look at paralleling of the devices, and just like we talked about with them in series and being able to balance the voltages, she looked at them in parallel and being able to balance the current. And we published a paper or two on that, but you asked about short circuit.
Yes, sir.
And I don't think we've done any work looking at it from a short circuit and having devices in parallel. No, I don't think we've looked at it from that perspective.
Okay.
I think it certainly can be done, and it's I don't think there are huge issues there, but certainly some things that you'd have to consider.
Okay. One more question.
Yes.
Did you have some short circuit evaluation for trench devices and comparing with planar MOSFETs? Any feeling of having some difference?
No, and I think I'm trying to think back to a talk I attended back this past fall. I think Dr. Baliga at NC State has I think he's published some papers on that. But I would look up. Dr. Baliga has done some certainly all kinds of work, and I think he looked at the difference in these two different devices there.
Okay, thank you.
Mm-hmm. Any other questions? Well, I really enjoy being able to talk to everybody. I think hopefully everybody got an appreciation for gate drives. it's funny. If you had talked to my younger self, let's say 10 years ago, 15 years ago, I had no real appreciation for gate drives. I just kind of viewed them as a nuisance and something that you had to do to use power electronics. I've since to gain, I call an appreciation and love for gate drives and realize how valuable they are and how elegant they could be in terms of how you use them. And so I do hope that you all have gained some appreciation, more appreciation for gate drives and realize that, you know, they can be your friend and you can do a lot with them. So.
Thank you very much, Professor Tolbert. I hoped Hansi would kind of round it up, but Hansi, are you there?
Yes, I am there, and I think this was a very interesting seminar, and we were very happy that you could give this to us. And if you would like to share your slides on the high voltage converters, we would be most happy to see that also at a later event.
Sure. Yeah, I'd be happy to do that some other time. And, you know, if, you know, those have been prepared already, so it's not that much work to, no. And that way that could kind of be a self-contained topic. It just, I had not done this long of a seminar before, and I wasn't sure about timing. And of course, it took a little longer than I thought it would or should. But yes, yeah, I'd be happy to do at some other date talk about the 10 kV work, because I think there are many things unique to the 10 kilovolts that you have to consider that you don't consider at 1200 volts. Yeah.
That's right. We have appreciated your seminar very much. And did you want to say something more, Mietek?
No, I just wanted to say that let's discuss it within the center, and then because Professor Tolbert already offered to make a second round or second part, so this would fit us very nicely.
Yes,
we can find a slot for that or a time, then we can continue. That was very impressive. It was a really long presentation.
Yeah, but interesting all the way through.
Yes.
So on behalf of the Wide Bandgap Power Center in Sweden and of the Power and Energy and Power Electronics chapter of IEEE in Sweden, we would like to thank you from our heart for this very interesting seminar, and we hope to see you soon again.
Well, thank everybody for attending, and I hope to see all of you soon at an upcoming conference. If not in 2021, then hopefully 2022. So everybody stay safe, take care.
Okay.
Thank you very much.
Bye-bye.
Thank you. Bye-bye.